The problem is threesome, and this is, you need to have solved 2-sum 2 to help with this, at least the solution I know of. So the idea is you're given an array of numbers, and you want to find all the possible combinations of 3 numbers that add up to 0. And you don't want to have duplicates, which we'll get into. So for example, with this test case, with this example they gave, what are the solutions? Negative 1, negative 1, 2, and negative 1, 0, 1. So for example, there's 2 negative 1s here, right? So you could technically, if you're doing this process, you'd actually find 2 versions of these, right? This would be the negative 1 at 0, and this would be the negative 1 at index 4. They don't want you to have both of those. That's a small detail, but we'll need to consider it. So the solution that I'm aware of, what you can do if you know 2-sum 2, right? 2-sum 2, the stipulation of that problem was that the array was sorted, right? That made the problem much easier. So, I mean, you could come up with an O of n cubed solution, right? For an element, for another element, and then for all the other elements, right? So you'd say for this guy, and this is the second guy, and then we want to say, okay, does this add this to it? Does it equal 0? Does this equal 0? And repeat that process. And then once you're done with that, shift this guy over, repeat the same process, and you know, O of n cubed. It's pretty brute force. It's pretty intuitive, even though it's not a good solution. You don't want to do that, right? So to kind of save ourselves from n cubed, we have to take a hit of n log n by sorting the array. Now, if we sorted this array, what we're looking at here will be something like this, actually. Get that negative 4 over there. So this is now sorted, so we're going to do this. All right. And now this makes the problem easier. This now looks like, well, it's almost like 2-sum 2, except we need 3 numbers. But the thing about this is, if we pick one number, if we say, okay, we're going to use this number, we need 2 more. Now we're doing 2-sum 2, right? Now we have a target value. So remember, all numbers a plus b plus c need to equal to 0, right? So if we know a is negative 4, then we know that b and c need to equal 4. Or put in a more general sense, the 2 other numbers need to equal the opposite sign of the first number. In other words, what we're saying is this is just 2-sum where the target is calculated by saying n times negative 1. So we're going to say for each number in here, all right, so 1 for loop for each number. So given number, this number is n. We're going to take the target, which is 4, and we're now going to use the rest of the array, the rest of the numbers, to do 2-sum. 2-sum 2 specifically because we're doing a sorted array. So we'll use the pointers, right? And we'll say, okay, if these 2 numbers add up to what we're looking for, then we can save this result. Now, right now this adds up to 1. So which means we need to increment this, the left pointer. Okay, still adds up to 1, adds up to 2, adds up to 3, and then we can't put them together because it's you can't use the same element. So adds up to 3, okay, we can't do it. So we'll move the n pointer, right? And we'll set this to n plus, the current number plus 1, because we don't want to consider the current number. So okay, we want to find our target now is actually 1 instead of 4. So we say, okay, negative 1 plus 2 is 1. Okay, that's a solution. Let's mark that down. Negative 1, 2. Okay. Now, is this a solution 2? No. Okay, that's actually, I kind of just skimmed over that. The question is, once we find a solution, in 2-sum 2, as soon as you find a solution, you're done, because there's exactly one solution. In this problem, you want to find all the solutions. So if we're at this point, we found a solution, what do we want to do? Well, it really doesn't matter, right? We could increment this, Or we could decrement this. It's the same difference either way, right? Now, why is that? I'm trying to remember why that even is. I just know it. I don't know why. Like, say that was a really big jump. Say this was a really big jump, like 4. So right now your solution is 5. You go here, it'd be 10. As opposed to going here, 5, 4, 3. I suppose because at some other point in time, you'll still hit all the numbers you would need. I'm not really sure how that works, to be honest. I just know it does. Why does it not matter which one you increment when you find a solution? Because increment there, you get 10. If that's still too high, so let's say what we're looking for. Let's just say, let's just say this was -7. So we're looking for 7 or 5. So this would have been -5. Okay, if we're looking for 5, this would be 5. Okay, great, we found a solution. So let's just increment this one. Now we're at 10. That's too high. I guess it doesn't matter because no matter what, no, I guess no, that wouldn't make sense. Oh, I almost had it. I guess it doesn't matter because, it doesn't matter because this solution here, -5, -1, and 6, because this is kind of set in stone for this current iteration. If you moved this one, then this other number is -1, right? So that's still this. Because you know the two numbers here, right? That means the only other number you could ever have is 6. And we don't care about that because we don't want a duplicate solution. So it doesn't matter which one you move, because what it comes down to is no matter what, at some point you'll have to move both of them, right? Because let's say we leave it here. So this is a solution right now. We want to move it because we found a solution. If we move this, there is no way to ever find another solution that's unique without also moving this one at some point, right? Because the only number we could find over here would be another 6. And if we found another 6, we wouldn't want to use it anyways. Same over here. We move this, we would need to find another -1. We don't actually want another -1 because it's not unique. So at some point you'd need to move both. Okay, that's why that works. That makes sense. But yeah. So also, an important thing to mention is to avoid duplicates. Right? So if we're here, we found a solution, we'd go here. Like I was just saying, we don't want this other -1, so we'd actually move again. So within the code, we'll just say, when we're incrementing this, we'll say, assuming we're moving the left one after we find a target value, we could very likely be moving the right one. It's the same idea though. The idea is after you find a target solution, you want to increment or move one of the pointers, and as long as that one equals the previous one, you want to keep moving. So that'll get us here. Okay, and then if we ever run into each other, then we're done. We can increment this again, so on and so forth. And we'll do the same thing with the end node, right? As long as, so let's just say we're here and we're moving on. As long as this equals the previous one, we'll keep moving. Right? So let's implement this. So we want our answer set first. We'll say for each number in nums, remember that's the first number over here, this yellow dot. What?
We're running on ours.
Okay.
We'll be back. You have your phone by you?
Yeah.
Just in case for some reason Fritz calls and he says it's on his way, I'll let you get a heads up so you can
Okay.
Keep an eye out for them. Are you doing work or something?
I'm recording videos for a thing.
Okay. All right. Bye.
Goodbye. Okay. So for each number in nums, we need to find the target, right? The target would be just negative n. Then we set our left pointer, which would be, actually we need to keep track of the I as well. So we just use Python's enumerate. So this would be I plus 1, and then right would be obviously the end of the array. So we'd say while left is less than right, as long as we haven't crossed each other or land on the same one. Again, we can't land on them because we can't use the same element. We'll check. We'll actually grab the total first. Nums left. So if total equals the target, then we found a solution. So we'd add that solution to the answers, which is a list of the given number, the left number, and the right number. And this is what I was talking about here. This is where we need to increment or decrement. We need either increment left or decrement right. So it doesn't really matter. Let's just do right. So we say right minus 1. And now as long, I believe as long as the current number at right equals the previous one, which, because we're going left, right to left, would be nums. Oops, that needs to be 2 equals. Nums right plus 1. As long as these equal the same thing, we want to keep going. That just gets us to avoid duplicate values. Now, otherwise, if total is greater than target, we need to lower the number. So we'll say right decremented. Otherwise, if total is less than target, we want increment left. Now that takes care of a lot of the problem, but one thing we need to do is deal with duplicates in n. What we want to do is check, if the previous number, rather if the current number equals the previous number. Of course, you don't want to get an index out of bounds error, so we also need to make sure that I is greater than 0, so we can actually do this minus 1 check. Okay. So this takes care of our duplicates in the two-sum part of the problem. This takes care of our duplicates in the first number. We add the answers. Is that? I feel like I'm missing something. Let's just run it and see. We also need to sort it. If we don't sort it, it's not going to work. Okay, nice, solid. We'll continue if this happens. Just going to keep running until we get a number that's not the same. Okay. Output 0, 0, 0. What's going on here? We got 2 of our answers, but then we got some nonsense as well. It's saying 2 plus 2 equals negative 4. What's going on here? I think this needs to be, the I comes first. No. Better, but now we just have a duplicate answer. So that was a problem, just wasn't the only problem. We have a duplicate answer here. As long as n equals nums, the previous one will keep going. Keep going here. How do you avoid the duplicates? Why is that not working? Negative 1. We have a duplicate answer. I thought we took care of the duplicates. If total equals target, we'll append it, great, and then we'll say decrement the right as long as the current right equals the previous right. Keep going. What am I forgetting here? Total is greater. I do not remember. Oh, not sure why that would cause this issue, but let's just see if it solves it. No, okay, that wasn't the main issue. I was about to say, I would have gotten an error if that was the issue. What's the problem here, though? Am I blind? Okay, for I, n, and enumerate nums, if n is greater than 0, if I is greater than 0. Now I just want to do this to show that this also needs to be there, but let's see what error we get if we don't have it. Okay, that accepts. It won't accept on all of them though. Yeah, exactly. Out of range. So what's happening with this one? So we have zeros. We're saying, okay, here's our n, here's our left, here's our right. We'll say, is this a solution? I think it's supposed to be a solution, right? We'll say, okay, this is a solution. Now let's decrement right. Is it the same? It's the same. Okay, it's the same. And now we're at the point, we're past the array. So what we need to do is say, you know, if we hit the point we're at the same number, then obviously we don't have any more different numbers we can use. So we just need to be done with that, which means if we added this, right, we'd say, okay, we have no more numbers. We'll break out of this loop. We'll run up here. We'll say left is less than right. It's not. Okay, we'll be done. So that's how that works. Cool.